Hello everyone, and a massive welcome back to this explainer on software engineering. Today we're focusing squarely on chapter 21 of our source text, and we're looking at the design of embedded real-time systems. As software engineers, it is just incredibly easy to get completely wrapped up in the purely digital world of code and algorithms. But today we are bridging the gap. We're going to look at what actually happens when our software has to interact directly with the messy physical world. This is a foundational topic for your understanding of modern systems engineering, so let's get focused and prepared to master these critical concepts.
Okay, let's dive right into our syllabus for today's explainer. We're going to cover an introduction to real-time systems, hard versus soft real-time, the core features of embedded systems, the stimulus response model, process design and shared buffers, and we'll wrap it all up with a lecture summary and exam review.
All right, Section 1, Introduction to Real-Time Systems. And as we'll see, it's about way more than just speed.
To start things off, we really need to clear up a common misconception that catches a lot of students out. When you hear real-time, you probably just think really fast, right? Well, let's look at the actual definitions. First up, an embedded system is a software system embedded in a hardware device that reacts to events in its environment. The software is literally built into the hardware, often in read-only memory. Economically speaking, these things are absolutely huge. Think about it. Almost every electrical device you touch today, your microwave, your mobile phone, your car's anti-lock brakes, they all run on embedded software. In fact, our source notes that in developed countries, there are literally dozens of embedded microprocessors for every single person. They are everywhere.
So then, what exactly is a real-time system? Well, a real-time system is one where correct operation depends on both the results produced and the strict time or deadline at which they are produced. This is a massive distinction. Real-time doesn't just mean fast, it means having an uncompromising deadline. A mathematically correct answer delivered a millisecond after the deadline is a total system failure. The textbook gives this brilliant example of a car's braking system. If the embedded software controlling those brakes takes just a little too long to process an input and actually apply the brakes, it doesn't matter if the calculation was flawless. You're still going to crash because the response was too late.
Let's do a really quick recap of our first section before we move on. Remember, embedded systems are all about interacting directly with hardware in the physical environment, and real-time systems are fundamentally governed by time. It's that strict adherence to deadlines, not just raw processing speed, that truly defines them.
Moving right along to Section 2, hard versus soft real-time. Basically, failing gracefully versus total failure.
Now, this brings us to a vital dichotomy that is highly likely to appear in your exams. We need to look at hard versus soft real-time systems. The absolute crucial point here is the consequence of missing a deadline. In a soft real-time system, if a result isn't produced according to the timing specification, the system's operation is just degraded. Think of a streaming video. If a frame is processed a few milliseconds late, the video might lag or buffer, which, sure, is annoying, but the system hasn't catastrophically failed. However, in a hard real-time system, if results are not produced strictly on time, it is considered a complete and utter system failure. Going back to our car brakes example, if they failed to deploy before the deadline, that is a total, potentially fatal failure.
Just to cement that knowledge in your minds, soft real-time means degraded operation when late, while hard real-time means complete system failure. Please recognize this difference. A very common student pitfall is failing to articulate just how severe missing a hard deadline actually is. You absolutely must be able to define this distinction clearly. All right, Section 3, Features of Embedded Systems. We've got 5 key differences to run through.
We know they are strict deadlines, but how else do these systems actually differ from standard data processing software, like a word processor or a web app? The source text outlines 5 specific ways. Difference 1, they generally run continuously. Unlike an app where you just click the X to close it, embedded systems usually start the second the hardware is switched on and just run indefinitely until powered off. Difference 2, they must react to unpredictable environments. A desktop application essentially controls the pace of user interaction, but a real-time embedded system has to concurrently handle both expected periodic events and completely unexpected, unpredictable events at any given moment.
Now, what's really fascinating here is how the physical world dictates the software. Difference 3 highlights severe physical limits. You might have crazy strict constraints on battery power, physical size, or weight, which forces you to write incredibly efficient code. Difference 4 is direct hardware interaction. You just don't have the luxury of generic device drivers provided by an operating system like Windows.
Finally, difference 5, safety and reliability completely dominate the design. Because hardware failure can have such high human or economic costs, software engineers take a highly conservative design approach to minimize risks, heavily favoring tried and tested techniques over newer, flashier ones.
So, to summarize our 5 characteristics, embedded software engineering is fundamentally constrained by the physical world. Your program must run continuously, handle the unpredictable, speak directly to raw hardware, sip battery power, and above all, operate with absolute flawless safety and reliability.
Let's hit Section 4, the stimulus response model. This is all about how the system reacts to the environment.
Given that embedded systems have to react to these wild, unpredictable environments, how do we actually architect them? Well, we use the stimulus response model. This is a design approach based entirely on cause and effect. An event in the environment, a stimulus, causes the software to react. The system processes this and sends a signal or message, a response, right back into the environment. In practice, stimuli usually come from sensors, like a thermometer or a motion detector. The responses are then sent to actuators, which are hardware components that actually physically change the environment, like switching on a cooling pump or triggering an alarm bell.
Now, let's see how this builds into 2 distinct types of stimuli that our system has to handle. First up, we have periodic stimuli. These occur at highly predictable, regular time intervals. For instance, the system might be programmed to poll a temperature sensor exactly every 50 milliseconds. It is super predictable. Contrast this with aperiodic stimuli. These occur completely irregularly and unpredictably. A classic example would be a user suddenly hitting a physical panic button, which triggers a hardware interrupt. The system must be designed to drop whatever it's doing and process this aperiodic stimulus instantly.
So, a quick summary of the model. Real-time systems are inherently reactive. We architect them using the stimulus response model so they can manage a continuous, steady flow of predictable periodic sensor readings whilst remaining completely ready to instantly handle unpredictable aperiodic interrupts. Doing both of those at the exact same time requires concurrent processing, which perfectly sets up our next topic.
Which brings us to Section 5, process design and shared buffers, or in other words, managing concurrency.
Because we have multiple stimuli arriving at all sorts of different times, a simple, sequential, step-by-step program just isn't going to cut it. We need multiple processes running at the same time, running concurrently. But concurrency introduces a massive challenge, and it's captured perfectly by this vital question. What on earth happens when a producer process, say a sensor generating data, and a consumer process, the software analyzing that data, run at completely different speeds? Think about it. If the producer runs way faster, unread data gets overwritten and lost forever. If the consumer runs faster, it might end up reading the exact same piece of data twice. We desperately need a way to coordinate them.
But before we can solve the speed mismatch, we have to establish a foundational ground rule for shared resources, and it's called mutual exclusion. This is essentially a coordination mechanism, ensuring that when one process is modifying a shared resource, absolutely no other process can access or change it. It acts like a lock on a door. You cannot have 2 processes writing to the exact same piece of memory simultaneously, because if you do, the data becomes hopelessly corrupted.
And this brilliantly illustrates the solution to our speed mismatch, the circular buffer. Let's walk through this one carefully. The buffer is an array of memory slots arranged in a circle. We use 2 pointers here, a tail and a head. The producer process always adds new data at the tail. The consumer process always reads data from the head. If the producer is working faster, the tail moves ahead, safely filling up empty slots. If the consumer catches up, it simply reads from the head. We use mutual exclusion, often via basic get and put operations, to ensure they never access the same slot at the precise same millisecond. This elegantly, perfectly prevents data from being skipped or duplicated, even when these processes are operating at completely varying speeds.
To recap this critical section, because real-time systems absolutely have to do many things at once, we use concurrent processes. To allow these processes to exchange information safely without data loss or duplication, despite running at wildly different speeds, we rely on shared, circular buffers protected by mutual exclusion.
All right, we made it to Section 6, lecture summary and exam review. Grab your pens. Please take out your notes because we are going to distill the absolute most critical facts from this explainer that you are fully expected to know for your assessments.
Number 1, you must be able to explain that real-time correctness depends on both the result and the strict deadline. Number 2, clearly articulate that missing a soft deadline degrades performance, while missing a hard deadline results in complete catastrophic system failure. Number 3, know the 5 ways embedded systems differ from standard software, paying special attention to their continuous behavior and severe physical constraints. And number 4, you must be able to explain the producer-consumer problem and exactly why a circular buffer is strictly necessary to manage concurrent processes safely.
I want to leave you with this somewhat provocative thought as we wrap up today. We've just learned how individual processes can safely talk to one another using circular buffers. But when you have dozens, maybe hundreds of sensors and actuators, how do you structure the entire system architecture so it doesn't just descend into absolute chaos? Well, the answer lies in state models. A very common way to model the overall behavior of embedded systems is using state charts, like Figure 21.5 in your textbook. Think of a digital petrol pump. Specific stimuli, like picking up the nozzle or squeezing the trigger, force the entire system to transition from an idle state to a pumping state. Understanding these state transitions is completely crucial for complex design, which leads perfectly into our next topic, architectural patterns for real-time software. Ultimately, I want you to remember that embedded systems engineering is a constant, thrilling tightrope walk between software architecture and uncompromising physical hardware limits. Thank you so much for joining me for this explainer. Study your notes closely, and I look forward to exploring system architecture with you next time.